AP 1, Unit 7, Lesson B, multiple choice, explained. Number 1, disk of known radius and rotational inertia, so we know the rotational inertia value, I, can rotate without friction on a horizontal plane around a central fixed axis. The disk has a cord of negligible mass wrapped around its edge. The disk is initially at rest. The cord can be pulled to make the disk rotate. Which of the following procedures would best determine the relationship between the applied torque and the resulting change in angular momentum? So the thing that we want to change is the torque. And measure the angular momentum. So if we know the angular momentum, we would need to know the angular speed to do that. And it looks like, so at least A, C, and D all measure the angular velocity of the disk. That would help us get the momentum. I want one that changes the torque. Now if I look at A, they change the torque, but why do they also change the time? That's going to mess things up. So you don't want anything that's going to change time. You want to apply that torque for the same amount of time. So if you look through your answers, which one of them does that? And I think D is our one. For five different forces, different magnitude, pulling on the cord for 5 seconds. They keep that as a control. And then measuring the final angular velocity of the disk. So D seems to make the most sense to me. We don't want to mess with time as well. That's another variable that's not factored in here. Solid metal bar is at rest on a horizontal frictionless surface. It's free to rotate about its vertical axis at the left end. So that dark dot is an axis. It's pinned down to a frictionless table. The figures show different magnitudes, forces of different magnitudes are exerted at bar at different locations, in which is the bar's angular speed about the axis increase at the fastest rate. In other words, which one has the largest alpha, which means net torque equals alpha times I. They all have the same I. They're all the same arrangement. So really, we're asking which one's got the biggest torque, biggest net torque. So we want the biggest force farthest away. All right, so let's go through these. Let's start with D. D's not going to work. In fact, D, this torque and this one are going against each other. So I don't see how that's it. These two are a good possibility because they both point in the same direction, produce the same torque in the same direction. This one produces a little less torque than this because it's closer. But still, this is a big force, but man, is it awfully close to the axis. So if it was being applied out here, it would be my winner, but it's really close. This force is only half of this one, but it's more than twice the distance away. And it's more force than these two. Even though these add up to the same force, this one is closer. So I'm going to go with A. I'm going to go with A. Mars moves in an elliptical orbit about the Sun, and the mass of Mars is much less than the mass of the Sun. At the instant shown above, Mars is getting farther away from the Sun. How does this affect the potential energy of the Mars-Sun system and the magnitude of Mars's angular momentum with respect to the Sun? So first of all, angular magnitude is not going to change because for the system, all the forces are internal, so the angular momentum is not going to change. So right away, I'm down to either this choice or this. Now, potential energy, not total energy, but potential. As it goes this way, that distance between it and the Sun is increasing, so the potential energy is increasing. MGH, H is getting farther, so I would go with B. The letters aren't here, but that's B. The system consists of a disk rotating on a frictionless axle. Okay, this is a lot of words. I've seen this problem before. This is a lot of words for what really is a simple question. So a system consists, this actually the first sentence is most important. A system consists of a disk and the clay moving towards it, as shown in the figure above. The outside edge of the disk is moving a linear speed of who cares, and the clay is moving at v/2, who cares. The clay sticks to the outer edge of the disk, okay. How does the angular momentum of the system after the clay strikes compare to the angular momentum of the system before? Well, the system consists of both. In the beginning, it had two angular momentums. The clay actually has what's called an angular momentum, and so does the disk. It's possible for an object moving in a straight line to have an angular momentum. Trust me on that one. If I haven't explained it to you in class, talk to me about it. Ask me about it. So this is just a conservation of momentum question. All the speeds, it's all not important. It's got to be the same because there's no external torque acting on it. All the torques are internal to the system. So the angular momentum is going to be, because the system is defined as both the clay and the disk. If we just looked at the disk, it'd be a different story. But they look at both as the system. So the angular momentum is conserved. It's the same, beginning and end. Diagram above shows a view of a child of mass m on a circular platform of mass 2m that is rotating counterclockwise. Assume the platform rotates without friction. So it's one of those merry-go-round things you find at local playgrounds. Which of the following describes an action by which the child will increase the angular speed of the platform, child system, and gives the correct reason why. So, first of all, the whole system has an angular momentum of I omega. We want it to spin faster. Remember, angular momentum is conserved. So if we make this value, I, go down, this has to go up to compensate in order to keep this the same. What's going to make inertia go down? Well, the more the child moves towards the center, that would do it. That would mr squared, r would go down, the I of the whole system would go down, and therefore angular momentum would go up. So we want the child to move towards the center, and that will decrease the rotational inertia of the system. So B is the correct answer. It will not change the angular momentum. That is a constant, because everything's internal. If you know that the figure skater, when she brings her arms in, or he brings his arms in, and they spin faster, then you should have been able to get it down to A or B as a possibility. And if you believe conservation of angular momentum and it doesn't change the angular momentum, you probably could have gotten to B, even if you're not sure what the person walking towards the center would do. The moon is in an elliptical orbit around a planet as shown above. At point A, the moon has a speed mu a and a distance ra from the planet. At point B, the moon has a speed of mu b. Which of the following, we call that a v, I don't know why we're using mu, but all right. Which of the following explains a correct method for determining the distance of the moon from the planet at point B in terms of the given quantities? I'm not crazy about this question, but first of all, conservation of angular momentum has got to be true here. So I would lean towards an answer that goes with conservation of angular momentum. And this is one of those questions where conservation of energy, like, for example, because the gravitational force exerted by the moon on the planet is the same as the exerted by the planet on the moon, while that is true, that isn't pertinent to this situation. The best answer is B, conservation of angular momentum, because the gravitational force exerted on the moon is always directed towards the planet. And because it's always directed towards the planet, you know that the angular momentum is going to be held constant because it's perpendicular to that. So it's not going to, B is your best answer. Not an easy question at all, really. Because a lot of the stuff looks true and is true, but isn't pertinent to the situation. Student conducts an experiment to determine the relationship between the applied torque and the change in angular velocity. Student used an apparatus shown as in the figure above, consisting of two discs that are glued together and mounted on a horizontal axle. Blocks of varying mass are hung from the string wound around the smaller disc. The blocks are released from rest, exerting different torques on the disc, and are allowed to fall a fixed distance. For each block, the time of fall t and the angular velocity, okay, so that's no big measure, and so they get the applied torque versus omega over t. Okay. This next sentence is the most important one. There is considerable friction between the disc and the axle. Which of the following best represents a plot that could be obtained? So that means that if they hang a paper clip from here, it isn't moving. So you need to get to a certain applied torque before this thing will even start to react. You hang a styrofoam ball, nope, not going to do it. You hang 2 styrofoam balls, nope, not going to do it. Yeah, there's a certain mass at which it'll then start to speed up. So one of these graphs shows a situation where the input doesn't create an output for a while. And that's going to be this one. Because for a while you can put a torque on it and it ain't doing anything. And then at some point it will start, and I would expect the angular speed to go up. So, yeah, for a certain amount of time. So yes, then I would go with this as my best answer, mostly because of that feature right there. I certainly wouldn't expect this. I wouldn't expect the speed to go down. This shows this thing starting right as no matter what you hang, it's going to start on there, and that's not true because there's considerable friction. So that's our best answer. Classic question. 2 objects released from rest at the top of ramps, same dimensions shown in the figure above. The sphere rolls down without slipping. The block slides down without friction. Which of the following reaches the ramp, bottom of the ramp first? It's going to be the one that slides because it does not have to give up any of its translational kinetic energy to rotational. So it's going to be the block. The block because it does not gain rotational kinetic energy, but the sphere does. So this is your best answer for that one. They start with the same potential energy. The spheres goes into kinetic energy translational and some kinetic energy rotational. Well, this is the only one that controls speed, so it's going to not make it to bottom as fast. This one, it only goes into kinetic energy translational, so it's going to have more speed to get to the bottom first. Student on another planet. Now we're dealing with problems from students on other planets. Can't they do their own work? Has 2 identical spheres, each with a mass of 0.6 kilograms attached to the ends of the rod of negligible mass. The student gives the assembly a rotation in the vertical plane and then releases it so that it falls. As shown in the top figure above, the sensors record the vertical velocity of the 2 spheres, and the data is shown in the graph as v is a function of time t. Another student wants to calculate the assembly's angular speed and the change in linear momentum of the center of mass of the assembly between 0 and 0.3 seconds. Which of these quantities can be determined from the graph? I can get the angular speed. If you give me the period of rotation, the time it takes to go around once, I know that's 2 pi radians. So all I need is the time to go around once. And I can get that. For example, here to here, I can measure that time. Whatever this time is, would be the period of rotation. So I can get that, which I can use 2 pi radians, and boom, I can get the angular speed. So definitely angular speed I could do. So it's either A or C. Now, linear momentum is mass times velocity. Well, I need the velocity of the system. Well, I can get that. It's just the best fit line here through the middle of these. I could get a value of that would be the velocity of the center of mass at any given moment. And then I know the mass of the system because I know they're both 0.6 kilograms, so that's 1.2 kilograms. And I could find the angular momentum. The linear momentum. So I would go with C.